So Alex will give it a second. Distribution of isogeny Selmer.
Great, thank you. So I want to start off dovetailing with what Neven just talked about in terms of, well, giving sort of global statements that complement the local statements. And the thing I want to focus on is something which I know as the Greenberg-Wiles formula. Other names for this include the Wiles formula, the Greenberg formula, no name at all. It probably should be called the Tate formula. I'll refer to things as Tamagawa ratios. That, in other words, like I don't know the name of like Tate duality, and I certainly don't know the name of what this is. So whatever you want is fine. So the setup is you have a global field. And normally when I say global field, I'm really thinking about number fields. This particular setup happens to work for function fields without too much hassle, so you can think about a function field if you would like. And take M to be a finite GF module. So just as yesterday and just as in Neven's talk, GF will denote the absolute Galois group of F, so the Galois group of a maximal separable closure. Separable closure. And the one restriction I'm going to make, because I said global field, is I'm going to assume that the characteristic of F does not divide the order of M. Okay, so this is a Galois module, and the objects that I like considering when I'm thinking about Selmer groups are Galois modules decorated with local conditions. So for each place V of F, we're going to choose a subgroup L of V inside of H1 GV of M. So GV being the absolute Galois group of the completion of F at V. And we're going to assume that LV is equal to the unramified cohomology for all but finitely the many V. So this is just a sort of sanity assumption to prevent very strange Selmer groups. And from this data, you can define a Selmer group. So the Selmer group of a decorated module is going to be similarly to the n Selmer groups that we defined yesterday. This is going to be the kernel from H1, the global cohomology group of M, H1 GFM. And then at each place V, we're going to look at the local image inside of local cohomology, and we're going to check that it's in LV. And so these LVs are sort of called local conditions because what this Selmer group is it's the set of global classes that obey certain local conditions, the ones that map into these local groups LV. Okay, so this is one key object associated to a module decorated with local conditions. The other one is the dual module. And so the dual module is again going to be a module decorated with local conditions. And so the first part here is I need to tell you what the module is. And it's going to be the set of homomorphisms from M to F bar S. So the separable closure, oh, one of these is unnecessary and I need that. So the separable closures units. How I usually think about this is the Tate twist of the Pontryagin dual. That's an equivalent way of writing this down. I want to give this some local conditions. And so what I'm going to, the local conditions I'm going to give it are, I'm going to give it, local conditions of LV perp. And so this denotes an orthogonal pairing. And so where LV perp is the orthogonal pairing, or sorry, the orthogonal complement. Complement to LV under the Tate duality map So this is the map that Niven defined in last talk, at least for the p-adic case. But as he said, you can extend this to the Archimedean places no problem, and also to, well, I hope you can extend it very easily to local fields in positive characteristic. This statement's still true, and that's it, right? I think. Okay. Okay. So this is how you can define a dual module with dual local conditions. And the fun fact, and the sort of the crucial fact, is that if we consider the size of the Selmer group with the local conditions we set before, to the size of the Selmer group of the dual, well, first off, both of these terms are finite. This term is finite because we required all but finitely many of these local conditions to be the unramified local conditions. That's enough to establish finiteness. And similarly, under this dual construction, because as Niven said, the orthogonal complement to the unramified local conditions are the unramified local conditions, so long as M is good at a given place. They also obey the finiteness assumption there. So these are both finite. And the point is that we can find the ratio. I like to denote it T for Tamagawa. Again, that's still not really the right person to give credit for this, but that's okay. And the formula is that it's equal to the size of the invariance of M over the size of the invariance of M check times some local terms, which account for these groups LV. So the size of the local conditions LV over the size of the orthogonal local conditions. And then this 1/2 is just to account for the fact that because we both have LV and LV perp in here, when we double the size of LV, LV perp goes down by 1/2, and so we would end up with a factor of 4. We need to get rid of that. That's why there's a square root. Okay. And so we have this formula which gives us some information about how global cohomology behaves just in terms of local information. And this turns out to be very relevant in an arithmetic statistics situation because it can force Selmer groups to be large for no other reason. Just because this ratio gets big, we find that the Selmer group has to be big. And so the key example of this, and the one that I'm going to carry sort of throughout the rest of the talk, is if we take E to be an elliptic curve over Q, and if we take phi to be an isogeny, so this is going to be a fixed isogeny of degree 2. We can actually decorate the kernel of this isogeny with local conditions. And the local conditions for that are they're going to just be the kernel of the map from H1 GV of E phi to H1 GVE. Okay, so this is a module that has been decorated with local conditions. And what's typically denoted as the isogeny Selmer group is, in fact, the Selmer group of E phi with these local conditions. Okay. And another fact that we have in this situation is that, well, we have this decorated module EC with local conditions, and we can consider its dual module under the setup that we have there. And what that actually looks like is, well, here's our diagram of E going to E naught. We have a degree 2 isogeny going one way, and then completing the multiplication by 2 is a degree 2 isogeny going backwards. So the composition of these two maps is multiplication by 2. And so this is an isogeny defined on E naught. And so this decorated local module is equal to the kernel of E naught phi naught with the local conditions associated to that isogeny. And so in particular, what the Greenberg-Wiles formula gives in this case is it gives us a formula for the ratio of the size of an isogeny Selmer group to the dual isogenies Selmer group. And so specifically, what we get is we get that the size of the Selmer group of E, of the phi Selmer group, compared with the size of the phi naught Selmer group of E naught, this is equal to, well, the H naught terms cancel, it's just 2 over 2. And then the local terms, you can do that out, and it's equal to the size of the co-kernel of the map EQV mapping to E naught QV over the size of the co-kernel of the other isogeny. Let me check to make sure I put the right thing on top. I did, or I didn't in these notes. But yeah, so one thing that can happen is you can end up in situations where this right-hand side explodes, and then you end up with a set of isogeny Selmer groups that also have to explode. And this can happen in quadratic twist families. The next thing I want to talk about is how local conditions change in twist families. And so, just as before, I'm going to set a 2 isogeny phi from E to E naught. And I'll take E to be a non-zero element inside this kernel. So this is a uniquely chosen, a uniquely defined element. And so what I want to note is that this is an element in 2 torsion, and so Galois theoretically it stays put when we twist this picture. So if we instead look at ED, E1 still lies inside of its 2 torsion, and it's still a rational 2 torsion point. And so for this reason, we can again kill the module generated by E1, and that defines a well-defined isogeny. So for every for every integer, non-zero integer d, we get an isogeny ED to E naught D, just given by killing E1. And for all of these, I'm going to use the same letter. I'm going to call all of these phi. And so the basic question that we want to answer is, as D varies, how does the isogeny Selmer group associated to phi vary? And the starting point here is, yeah, let me actually write that down. And I guess I started over a general global field. I'm just going to assume everything from here on in is going to be over K. And so the starting point is to take advantage of the fact that under quadratic twist, the point E1 remains rational and stays put. And so because of that, the kernel of this map stays put as a Galois module. So the starting point is we have self ED lying inside of the first cohomology group of E phi. But this is just a copy of F2. It is just a copy of the trivial module with two elements. So this is exactly the same as the set of homomorphisms, GQ to F2. And this can be identified with square-free classes of numbers. Under the Kummer map, or under the isomorphism that I gave yesterday, where if you have a D here, to get an element in here, you look at sigma root D and see if it's different from root D. Great. And so under this, we have that the phi Selmer group is going to be some subset of Q cross over Q cross squared, and it's going to be cut out by local conditions. And so there's three basic ways that those local conditions behave. So first, we can have phi is good for E. So by good here, I mean that it's a prime of good reduction for E, and it's not either 2 or infinity, which are sort of special cases. So V is good for E, and furthermore, V does not divide D. So in this case, the local condition associated to V in the Selmer group is just that your cocycle better land inside of the unramified cohomology. So in terms of if we want to check if a given B in the square-free classes lies in this set, we just need to check that V does not divide B, assuming B is square-free. So for all of the good primes for ED, that is to say that they're good for E and don't divide D, we just need to check that our associated B Q cross over Q cross squared isn't divisible by that V. Or maybe more precisely, has even valuation at that V. Okay, so that's the first sort of type of local condition. The second type of local condition that comes up is V is bad for E. So again, this means bad reduction or is one of 2 or infinity. So in this case, there's not a lot we can say. The thing that we are going to take advantage of to handle these primes is these bad primes don't shift around as D changes. So let's say there's 7 bad primes at the beginning of our problem. No matter what twist we look at in this family, there's still going to be the same 7 bad primes. And it's, a little annoying to deal with them, but it's a finite problem. And so somehow they aren't the main players in a calculation like this. Really, the main players are in the case that is left, which is if V is good for E, but V divides D. And again, I'm thinking of D as a square-free number, so that V divides D means it has a pot valuation of V. And just so I don't go crazy, let me change V to P, because these are just terms. Okay, and so this is the case that we must control. And we must control it because as D changes, this set of primes grows sort of arbitrarily large. And we'll go through this particular calculation in some detail because I do think it is extremely important to understand in order to understand really how these two Selmer distribution questions are answered. And so the key sequence to look at is, well, we're looking at the local conditions that we've attached to our isogeny's kernel. At a given P dividing D, that's good for E. And this, by definition, is the kernel of the map from H1 GP E phi going to H1 GP of E. So that's how we defined it. And now the first reduction is, since P is odd, we actually don't need all of E in this term here. We get the same exact kernel if we restrict to just the to infinity part. So just looking at the torsion. Oh, I forgot a D, that's super important. D's everywhere. Okay. And so I think of this result as being by Bloch-Kato, but of course it's much earlier than that. But certainly it comes up in the Bloch-Kato argument. The idea that if you want to know the local condition for a Selmer group, an elliptic curve, it suffices to look in the torsion module except for the primes dividing, well, in two in this case. So this is safe. Great. And so now I want to flip this around using the long exact sequence sort of associated to the isogeny. So E phi maps into the to infinity torsion of E phi, and the quotient there is E naught to infinity. So we have this exact sequence of Galois modules. And when we consider the long exact sequence associated to it, part of it reads H1 GP of E d phi. I've yet again forgotten to twist these. H1 GP E d phi into H1 GP E d to infinity. And this can be just reinterpreted as the image of some connecting map. H1 H naught GP E d to E naught d to infinity going under a connecting map that I'll denote by delta D to H1 GP E of phi. Okay. Great. And so the next thing I want to note is that if we take a look at E naught d to infinity, and we consider the part of it which is fixed by the inertia group at P. Well, let's think about this. If the D wasn't here, this inertia group would fix this whole entire module. Since the D is here, we know exactly how the Galois structure of this relates to the original one. It's via this twist of by a quadratic character associated to D. And so what we find is whenever that quadratic character acts non-trivially, this on a given element in this set, the action of IP also has to be non-trivial. But the portion of this that's sort of fixed by the relevant automorphisms of plus minus 1 is just the 2 torsion. So this set of invariants is equal to E naught D2. Oh, which is just E naught D2. And so, in particular, the part which is fixed by the entire Galois group above P must also be fixed by inertia. And so, in this connecting map, we can replace H naught GP E naught D to infinity by just this 2 torsion part. So this, a local condition, is equal to the image of H naught GP E naught 2 inside of H1 GP E phi. Well, at this point, I actually don't need the D, except here, that the image is with respect to the connecting map twisted by D.
Can you explain why we have the last equality that E not D2 is unramified?
Sorry, what was
Why
it?
is E not D2 IP equal to E not D2?
Oh, this. So this is because we're in case 3. So we've assumed that we're dealing with a prime that's good for our initial elliptic curve E. And so because of that, and because E naught D2 is isomorphic as a Galois module to E naught 2. Yeah, that's the crucial step, is that this is isomorphic to E naught 2. And E naught 2 is unramified as a Galois module because we assumed P was good for E, and hence for E naught. That's a great question, yeah, thank you. Okay, so what I want to do is I want to understand a little better how this connecting map behaves. And how I will do that is by sort of looking at the exact sequence it's associated to. So this connecting map is associated to the exact sequence of E phi maps into E d phi, oh sorry, E d2 phi. And then the quotient of this is E naught 2. And I'm skipping writing the D's on the right and left because both of these are inside of 2 torsion, and so the quadratic twist has no effect at the level of Galois modules. Okay, and so the connecting map delta D is calculated with respect to this exact sequence. But we could also consider the connecting map associated to the exact sequence through E2 phi. So we also have this exact sequence. And these are very closely related exact sequences. They only differ in terms of the quadratic twist that we put on this module E2 phi. And so what we find is, well, the first thing we find is that delta D of this fixed point E1, this rational point on, oh, sorry, this would have to be for delta D associated to E1 prime. This is going to equal delta 1 of E1 prime. So here, E1 prime is defined to be the generator of the phi torsion, of the phi naught torsion, so of the dual model. And so the reason why you expect this equality to hold is that if you look at the sequence and you consider something in the phi naught torsion of E naught, that fits into the subsequence where we have E naught phi naught. That goes into here. Then we have 2 torsion in the middle. And then phi torsion on the other side. And so in particular, because it's 2 torsion in the middle, the 2 torsion has no effect. And so for this particular element, the twist is doing nothing. So delta D E1 prime is equal to the untwisted version. And the second thing to note is choose some E2 prime inside of E naught 2 backslash E naught phi naught. So just anything outside of this module. Then if GP fixes E2 prime, in this case both delta D and delta 1 are defined. And what we find is that delta D of E2 prime is equal to delta 1 of E2 prime. Plus, this term is just going to depend on D. It's sort of measuring the difference between these 6 sequences. And in fact, it's always going to be of the form chi of D. So the quadratic character associated to D times E1. So basically a quadratic character valued in the phi torsion of E. And so how I think about this is, in this case, E2 prime does not lift to E naught phi naught. Instead, E2 prime lifts to something in here which is properly not in the 2 torsion. It's in the 2 phi torsion, but not the 2 torsion. And so, because it's not in the 2 torsion, it will feel an effect from the quadratic twist. And so will its co-boundary, and that's where this term chi E1 is coming from. So this is there's a couple different ways to answer this. I guess you would say E1 is inside of H naught of the phi torsion, and so this is a cup product. So you have a quadratic character, cup product, something in H naught of the phi torsion. But in my sort of setup, where I like thinking about both of these as sort of lying in square-free, in classes of square-free integers, how I really would prefer to write this down is that there's some, I would like to say that there's some integer coming from this, let's call it A2, so that delta D E2 prime, thought of as a square-free integer, is equal to A2 times D. So this is under the isomorphism between the phi torsions H1 group and Q cross over Q cross squared, is how I'm thinking of this. Similarly, thinking of things in terms of square-free, of classes of square-free integers, I think of this as saying that delta D E1 prime, this is also given by some fixed square-free integer that's sort of just set by your elliptic curve. Any other questions? So let's summarize sort of what's happening here. So we started with prime dividing D, that is good for E. And what have we found? So first, if H naught GP E naught 2 has size 4, and the size of H naught GP E2 is 2, then LP is equal to 0. So how is this? How am I showing this? What I'm doing is, if you have this condition satisfied, this is equivalent to A1 being a square mod P. And so this contribution to local conditions is 0. And meanwhile, this group has size 2, so this contribution to local conditions is the only one. So this part doesn't matter. In this case, we get LP equal to 0. Similarly, if this group has size 2, well, in this case, A1 is not a square. So if it's 2 and 2, what that means is that we have an unramified non-trivial class that shows up in the local conditions, but no ramified class. So in this case, LP is equal to the unramified cohomology for the feed torsion, which when considered in terms of Q cross over Q cross squared, that means we're looking at the square free classes that aren't divisible by P in the second case. Third, so the third, if the first cohomology group has size 4 and the second cohomology group has size 4, so in this case, this term is back to being trivial. Delta D of E1, this A1 is going to be a square mod P, so this doesn't contribute. But this now does, because E2 prime lives inside of the invariance under GP. So in this case, LP considered inside of QP cross over QP cross squared is generated by this A2 times D. And finally, if the first cohomology group equals 2, and the second one equals 4, this is the least restrictive case. Because in this case, this A1 is a unramified, non-trivial class, and E2 prime is fixed by GP, and so the second one gives a non-trivial ramified class, and together they actually generate all of this group. The maximal size of, well, the QP cross over QP cross has dimension 2. And so in this case, we really do get that LP is equal to QP cross over QP cross squared. And so these are what the local conditions look like at the primes dividing D that are good for our isogeny Selmer group. So the next thing I'll want to do is I'll want to actually use these to prove something statistical, to sort of sum over the size of an isogeny Selmer group in a family. But before I do that, I want to point out how the Tamagawa ratios, or the Greenberg-Wiles formula from before, is showing up. What you should be noticing is if you want your Selmer group to be large, then you should hope that most of the primes fit into this camp. And if you really want it to be tiny, you should hope that most of the primes fit into this camp. And somehow the difference in the number of primes between 4 and 1 seems like it would really influence how these isogeny Selmer groups behave. And this turns out to be the case. For example, if you start with an elliptic curve with a partial 2 torsion, so it has 2 global rational points in 2 torsion, but then its isogenous curve has 4 points in 2 torsion. Well, this case never happens, and this case never happens. So you only end up with primes in these two cases. And so what happens to 100% of the Selmer groups in that family of twists is that they blow up. You end up with Selmer groups whose average size is unbounded, and such that like 100% of them have rank larger than any integer you could choose. Similarly, you can engineer situations where the isogeny Selmer groups are tiny 100% of the time. For example, if you have an elliptic curve with full rational two torsion that isn't isogynous to another elliptic curve with full rational two torsion. In that case, you end up with these two types of primes, and so the isogeny Selmer groups you see have very restrictive local conditions, and they tend to be zero. But because that's all very complicated, and I want to focus on something that we can actually really get our hands on, let me enter a situation where only one of these types of primes can happen. And to do that, I'm going to assume from now on that E2 and E naught 2 are both only made of rational points. So both of these two torsion submodules have the trivial Galois action. In this case, you only see primes of type 3, and somehow that's sort of the most interesting type anyway. So, and so we'll go ahead and assume this from now on. Okay. Okay, and so the setup that I want to use is something that I like to call a grid. And so a grid of twists is going to be a set of integers whose prime factors come from certain axes that we fix ahead of time. And so maybe to make that specific, we're going to choose disjoint sets x1, xk of primes, and we're going to also take A to equal the product over all the finite bad primes of P. So this is done with respect to our elliptic curve E. So we have the product of all its places of bad reduction in addition to 2 if 2 is not a place of bad reduction. So take A to be this. We assume these primes that no prime in any xi divides A. Okay. And so with phi from E to E naught fixed as before, and under the assumption that I've put on the leftmost board, our goal is to estimate the size as we vary P1 through Pk inside of this product x1 up through xk of the size of the isogeny Selmer group associated to the twist of E by the product P1 through Pk. And so this is sort of the first instance of the formulation of a grid really taking a rule. The idea here is that we have this product space over sets of primes, and we're sort of using the bijection between that and a set of non-negative integers. So here we have a nice square-free integer that we've assembled one prime at a time from this list of primes. And so yeah, our goal is to estimate this quantity.
Are we assuming anything about the egg size? Could it be finite, infinite?
Definitely finite. In fact, I'm going to say that that's important enough to put on the first port, because in addition to that assumption, we do need to make several more if we want to have any chance of actually estimating this. But finite is, of course, sort of, you need to assume finite, or this doesn't quite make sense, yeah. Or I guess it makes perfect sense. It would be very easy. Anyhow, the assumptions that I want to use to estimate the sum. So one of them I put on the board over there. I'm going to assume this fact about the two-torsion. Another assumption that I'm going to use is that A over Pi is equal to A over P prime I. And I want this to hold for I less than or equal to K, and any two primes taken from xi, and for any divisor A of big A. And so this is a Legendre symbol. What I'm trying to impose here is I'm trying to say that at all the bad primes of E, I want every prime in xi to sort of behave the same, at least quadratically. Okay, so that's one assumption that I want to put on the situation. The second assumption sort of goes to Ariel's question, which is, in addition to assuming that these are finite, we better assume some extra stuff as well if we want to estimate this. And the second assumption is for I not equal to j, and any function c going from xi to the interval from -1 to 1. This could be the disk of radius 1 if you wanted in the complex numbers, maybe that's more traditional. We assume that the sum over all the primes in xj of the absolute value of the sum of all the primes in xi of c of pi times the Legendre symbol pi over pj. And now I'm going to be vague, is really small. Here, really small will be relative to the size of xi times xj, so the trivial bound that you could put on this quantity. And what really small actually means is annoying to sort of set up, because you want a lot of these terms to actually sum to something that's small compared to the main terms. So I don't think that's super interesting, so that's why I'm being a little vague here. But I will say that these sorts of things, these sorts of estimates are known. So this would be a large sieve type estimate. And an early version of this kind of thing that I've used extensively is a version due to Jatila from, I think, 1977. So since the 70s, people have been working on the large sieve, and they lead to all sorts of wonderful results like this, bilinear inequalities on characters. Okay. And finally, I have probably the weirdest looking assumption, but one that's necessary because I haven't really said much of anything about how the local conditions at the primes, at the bad primes behave. I basically just said they are what they are. And that's not actually Surprisingly, you don't need to say too much more than that if you're willing to make an assumption like the one I'm about to write down. So for any divisor of A besides 1, we're going to assume that A over pi, this Legendre symbol is -1 for some I less than or equal to k. And because of assumption 1, this would hold for any pi inside of xi. It's invariant across xi. Okay, so those are the 3 assumptions. And under these 3 assumptions, you can estimate this mean without too much trouble.
Sorry, I was wondering about the second assumption. Are we assuming that the xi is roughly the same size?
So what I would say is they can have whatever size they want if this thing is really small compared to the product of xi times the size of xi times the size of xj. But in practice, what that means is that the xi and xj, if you want to apply a Larsiv inequality directly, you would need xi and xj to have ballpark the same size. Where ballpark, so you know, means that you can't have one of these be logarithmic in the size of the other. That's too small. But anything better than that is usually good enough. Yeah.
Did you have like an example of a set of primes that look like 2, maybe just x1 and x2 that satisfies that? When would this be really small? Yeah. Just
Sure, yeah, so if you take the set of all primes up to h, and then you take, well, the same set actually, just if you make x1 and x2 the set of all primes up through h, and you just ignore the terms where you have a prime over itself in a Legendre symbol, this inequality, this is small enough, easily small enough. That's sort of the ideal case, actually.
But they're supposed to be disjoint. Maybe.
Yeah, so if you want 2 things that are disjoint, make x1 all the primes equal to 1 mod 4 in that range, and x2 all the primes equal to 3 mod 4 in this range.
Is that like a good way to, is there a tagline for the second one? The tagline for the first one is that 2 primes are the same with relation, they have the same local condition with respect to A. Like the second one's sort of saying that the collection of primes is suitably random or something? Or?
Yeah, so the tagline here, so this is, you're touching on a theme that actually turns out to be important even at higher Selmer levels. So something that we'll touch on Friday. How I like to think about it is the Legendre symbol is a bilinearly random invariant. And that's something that is super important for understanding the 2 Selmer group. Like if it wasn't bilinearly random, then you would run into all sorts of troubles actually calculating 2 Selmer groups, because basically what this says is, you're asking whether a given pi how a given pi affects the local condition at pj. The Legendre symbol measures that. If something like this doesn't hold, then you might not have independence of all of those local behaviors, and they could collude to ruin your Selmer groups. So this is sort of measuring independence of those local behaviors.
So the point is, it could go wrong if for some reason I change my sets in such a way that pi over pj is always 1.
That would be a very bad thing.
So I should think of it as sort of these 2 sets are randomly chosen enough to give me the independence of this.
Yeah, but again, this phenomenon where this is really small is super easy to get. The error terms that you see in the example I mentioned before, the 1 mod 4, 3 mod 4 example, are polynomial stavings. This is compared to something like the Cherepanov density statement, where Cherepanov density, the best you can do is some polynomial. You end up with x root negative root log h staving, if you look at all primes through h. So this is a really robust tool, and over the last decade of me working on this problem, I've relied more and more and more on inequalities of this type compared to other types. Yeah, if you can get something that looks like this might work, it usually does. Okay. So the crucial thing that sort of makes this calculation possible is that we can parameterize things that look like they might be Selmer elements. And so how this looks is we have a set V, and this is going to be the set of square-free classes of numbers A dividing A, together with subsets of 1 through K. And so this is a vector space over F2. The way you can see this is if you want to add two things together in this set, you take the product of their corresponding A's and maybe divide out by a square term that shows up. And then you'd use the symmetric difference to add together power sets. So, 1, 2 plus 1, 3 is then equal to 2, 3. So that sort of relation, we have this nice vector space. And for D, inside of this product of x's, of xi's, we can define a map BD from V to Q cross over Q cross squared. And this map will just send an element A and a subset T. Well, if we write D in the form P1 through Pk, it's going to send this to A times the product over all I and T of Pi. And so a claim is that any element in cell phi of ED, and here I'm being a little bit sloppy with notation. D, I said, was a tuple, P1 through Pk. Here I'm thinking of it instead as the product. So any element in cell phi ED is represented inside of this fixed parameter space Q cross over Q cross squared by something in the image of this parameterization BD. And if you sort of unwind what the definitions are saying, all I'm really claiming in this is that a Selmer element can only be ramified at the bad primes of V, including 2, and the primes dividing D. That's all that this statement is saying. But somehow this idea that we have a fixed space that we can use to parameterize things that look like Selmer elements throughout the grid, this turns out to be a really powerful notion and one that's very much worth generalizing to more difficult situations.
Isn't infinity show up somewhere?
What was that?
Isn't the infinite place show up somewhere?
Yes, it does in the sense that I didn't specify A had to be positive here, I guess.
Okay.
I think that's okay. Yeah, it is. Oh yeah, when I said bad, you need infinity as well. Yeah.
Okay, so it's a product of bad primes, and that could be minus it.
Absolutely, yes. Yeah. It has to be. It needs to be square free, just so that it's not redundant. But yeah, minus A is absolutely on the table. Okay. So if we take V naught, we'll take V naught to be the subset of V, satisfying such that B of D, V naught, satisfies the local conditions at all bad V. So this again is the primes where E is bad together with 2 and infinity. And so the claim here is that V naught, first that V naught does not depend on V naught does not depend on the choice of V inside of x1 through xk. And this is a consequence of the assumption I just erased, that at all these bad primes, the primes inside of xi all behave the same. And the second claim is that we actually have an explicit formula for V naught. I won't write it down, but the reason we have this explicit formula is you can think of V naught as parameterizing a particularly relaxed Selmer group, one where we've assigned any local condition, the maximal local condition at all primes dividing D. That's what the size of V naught is, if you sort of consider the definitions. Okay, so that's a really relaxed Selmer group. The dual Selmer group is then going to have very stringent conditions. This makes the local conditions at all those primes the 0 conditions, and because of this, we actually find that that Selmer group has to be trivial. And so, using the Tamagawa ratio calculation from before, that is to say the Greenberg-Wiles formula, you can exactly calculate the size of V naught. And so now, to find the average size of the isogeny Selmer group, we need to sum over this set V naught and over the set D in the product x1 through xk, but I'll leave that for next time, so thank you.
When you say V naught satisfies the local conditions at the bad primes, is it supposed to be like the biggest thing satisfying the local?
Yeah, it's a set of alls V and D such that BD of little v satisfies the local conditions.
So the image of V naught under BD, should that be like a relaxed Selmer group?
Absolutely, yeah. It's the Selmer group where the local conditions at all the bad primes of V and to infinity are satisfied, as for the isogeny Selmer group, but where at all the primes dividing D, besides the bad primes, it's any local condition, because we haven't yet restricted. We haven't yet imposed the local condition on those, but we have allowed ramification at those primes. I'm very proud of that final trick with the Greenberg-Wiles formula, because this is exactly the trick that allows us to sort of not care what happens at these bad primes. As soon as you know that the dual Selmer group has been, you've put enough conditions on it that it's trivial, you no longer need to care about anything else.